Let's take a look at the force on a moving charge in a magnetic field. Later, we'll utilize this to explain the operation of railguns, motors, mass spectrometry, and the Hall effect. We've already encountered forces between current-carrying wires. Here is the equation we had for the force on a differential current element in a magnetic field. Here I've rewritten this force on a current element IDL in a magnetic field H. Ampere had to deduce this equation by looking at the forces between current-carrying wires. Let's look at a charge Q moving with a velocity u. So every dt, the charge moves a distance dl. And so in the region of the charge, you can think of a current flowing as the charge at that location over the time dt. The velocity of the charge will be the differential length divided by the time dt. So for the current represented by this charge moving with the velocity u, we can substitute q over dt, and for dl, we can substitute the velocity times the differential time dt. So our dt's here cancel. So the force on a charge q moving with a velocity u in a magnetic field intensity h is given by this equation. Whereas Ampere had to deduce this equation from current-carrying wires to obtain the force on a current element IDL, we can do a much simpler experiment. We can have an ion moving with a velocity u in a magnetic field and observe the force it experiences. Now let me move the permeability of free space over to the right-hand side of our cross product. I'm going to identify this product of the permeability of free space with the magnetic field intensity as B, the magnetic flux density field. So with this identification, we can rewrite the force on a charge Q moving in a magnetic flux density field as QU cross B. In 1881, J.J. Thomson, who was the discoverer of the electron, published an equation for the force on a charge Q moving with the velocity u in a magnetic flux density field, but he got the equation wrong. Oliver Heaviside published the correct equation in 1889. As we did, Heaviside probably deduced this equation from Ampere's experimental observations that led to the force on the current element IDL. We will actually see the direct observation of this fundamental result when we look at mass spectrometers. Our electric field intensity was in terms of volts per meter. Similarly, the magnetic field intensity was in terms of amps per meter. Our electric flux density field was in terms of electric flux per meter squared, and electric flux had units of coulombs. So similarly, the magnetic flux density field is going to be units of magnetic flux per meter squared. Let's determine the units of magnetic flux. Looking at our force equation, we see that newtons will equal coulombs times meters per second times magnetic flux per meter squared. Solving for magnetic flux, we get meters, newtons, seconds over coulombs, and a meter times a newton will be a joule, and a joule over a coulomb is a volt. So the units of magnetic flux are volt seconds. I will use the symbol psi to represent magnetic flux, but you will often see the symbol phi used to represent magnetic flux. Since volt-seconds is the unit of magnetic flux, volt-seconds per meter squared are the units of magnetic flux density field. Now the volt-second is more commonly referred to as a Weber, so the units of magnetic flux density will be Webers per meter squared. But the Weber per meter squared is also referred to as a Tesla. So 1 volt-second per meter squared equals 1 Weber per meter squared, which is equal to 1 Tesla. Now 1 Tesla is a very large magnetic field, so another unit is sometimes used, the Gauss. And 10,000 Gauss are equal to 1 Tesla. Flowing from the sun is a collection of charged particles like protons, electrons, helium nuclei, and atomic nuclei of some heavier elements like carbon, nitrogen, and oxygen. The surface of the Earth is protected from these charged particles by the Earth's magnetic field. We know these charged particles will experience a force given by QU cross B. As these particles enter the Earth's magnetic field, they are deflected sideways and around the Earth. To find the amount of electric flux going through a surface, we integrate d dot ds over that surface. Similarly, to find the amount of magnetic flux going through a surface, we integrate b dot ds over that surface. If we integrate d dot ds over a closed surface, we know that we will get the charge enclosed in that surface. That is Gauss's law and one of our Maxwell's equations. What do we get if we integrate b dot ds over a closed surface? You have all played with magnets, and whether intentionally or accidentally, you've broken them, and what you found is that you didn't get a north and a south pole. What you ended up getting was 2 magnets. And if you kept taking one of the pieces and breaking it, you would always end up getting 2 magnets. In fact, if you got down to, say, an individual iron atom, you would find that that iron atom would act like a little magnet. When we visualized magnetic fields resulting from current-carrying wires, we found that those magnetic field lines always closed on each other. So we can't find a source and sink for magnetic flux density like we can for electric flux density, the charge. So the integral of b dot ds around a closed surface is going to be 0, and that will be our 4th Maxwell equation. So our 4th Maxwell equation is the nonexistence of magnetic monopoles. So the point form of this 4th Maxwell equation is that the divergence of B is going to be 0 because of the non-existence of magnetic charge. Let's visualize this. Here we're looking at a closed Gaussian surface. Since magnetic flux lines close on themselves, this magnetic flux line leaving the right face must re-enter the Gaussian surface somewhere so that it closes on itself. Since every leaving flux line re-enters, the sum of the flux leaving our Gaussian surface is 0. If we have both an electric field and a magnetic field, a charge can feel a force due to the electric field, and if it is moving, due to the magnetic field. This combined force is referred to as the Lorentz force equation.